All right. So what I want to do now is give a very brief and uh, simplistic way of talking about hypothesis testing. So, so let's take an example. Let's say we have two people. One's named Bob. Maybe they're friends. Maybe they're roommates. And one guy's name is Billy. Uh, and someone has to clean the dishes every night, right? So they decide to uh, do a coin toss every night. So if you get a heads, Bob has to wash the dishes, right? If you get a tails, Billy has to wash the dishes. So uh, 3 days go by, right? And uh, we get a heads every day, basically. So so 3 days in a row, Billy Billy has to wash the dishes. So that makes Billy suspicious. That makes Billy suspicious. Maybe because a coin is a 0.5% 0.5 probability, 50% chance of a heads and tails, and Billy is like maybe the coin is not a fair coin because 3 days in a row there's been a heads. I've been washing the dishes. Maybe Billy had a trick coin or something, and he didn't want to wash the dishes, and like I just have to wash it every night. I guess sucks for Billy, right? Uh, so how do we prove this claim, right? So the claim that Billy is making, right, is uh, and the claim is commonly known as the alternative hypothesis Billy is making is that the coin is not fair, right? So there are two ways of looking at it, right? The coin is either not fair, which is the claim, or that the coin is fair. And when the coin is not fair, we can kind of say that the probability of heads is not 0.5, not 0.5, is not 0.5, right? And the what we call the null hypothesis is the other possibility, right? Or the status quo, that the coin is indeed fair, and this is all happening by chance, is fair. So now, how do we test this claim? So getting three heads in a row is an unlikely scenario. So let's actually calculate what the probability of getting three heads in a row is, which is 0.5 cubed, uh, which ends up being equal to 0.125, right? So so there's a 0.125, which is a 12.5% chance that we get three heads in a row. Now, this chance, I mean, it's not a super likely scenario, but it can happen. It can happen. Like 12.5% chance can happen, right? It could be because of chance. Uh, so 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 I guess we could say that this evidence, like the chances are there, right? So like we can't just say that the coin is definitely not fair, or like uh, so we don't basically have enough evidence to suggest that the alternative hypothesis is true, so we can't reject uh, the null hypothesis or the status quo. Now let's imagine, let me create the background color. Let's imagine that 20 days go by and we get 20 heads. 20 heads. Now Billy is, sorry, it was Billy or was it Bob? Uh, yeah, now Bob is very suspicious now because 20 heads is even more unlikely, right? So now definitely like he's like something's off. So let's calculate the probability of this happening by chance, assuming that the coin was indeed a fair coin. So for a fair coin, the chances of getting 20 heads in a row would be 0.5 raised to the power of 20. Uh, and that's probably going to be a very small number, but let's calculate that. That is equal to that is equal to that is equal to 9.5 into 10 power minus 7, which is an extremely small number. Uh, an extremely small number. It's like 0.000000000 0 something 95, right? So that's the chance, that's the percentage of that scenario happening. A very extremely small possibility. uh, Now when the possibility is this small, well, not always this small, but like it's extremely small, uh, we can reasonably come to the conclusion that the coin is indeed not a fair coin, right? uh, so then we say that we reject the null hypothesis. We reject the null hypothesis, is known as H0. We reject the null hypothesis because the probability of this happening by chance is extremely low. Uh, Now, uh, so what's the threshold, right? So if the chance for, if we got like five heads or something or whatever, right? If the chance of that happening, the probability of that happening by chance was, let's say, 8%, would we still reject the null hypothesis? What if it was 5%, right? uh, so what statisticians use uh, is a metric called a significance level. So let's talk about that. Significance level. So significance level is basically that threshold, or that chance, right? Below which we reject the null hypothesis. So typically that is 0.05 or 5%. What that means is, if the probability of something happening by chance is less than 5%, we reject the null hypothesis, meaning we accept the claim. Well, we don't accept the claim, but we reject the null hypothesis, which means that the null hypothesis is most probably not true. Uh, and that and there's and so in this case, where we have this chance, so if we're using a significance level of 5%, then we reject the null hypothesis, as our probability of this happening by chance is much less than 5%. Or even if it was close to 5% but less than 5%, we would still reject the null hypothesis. Now let's just outline some steps, right? uh, so when we're dealing with a hypothesis testing problem, the first thing we want to do is identify the null hypothesis and identify the alternate hypothesis, the claim, right? The next thing we do is we assume that the null hypothesis is true. We assume that the null hypothesis is true. And then we try to, so we'll have a sample, or we'll have an event, right? Like for example, 20 heads. So we try to calculate we'll also be given a significance level, right? Which, or if you're not given, we assume 0.05. We calculate the probability of an event occurring, don't mind the bad handwriting, occurring given that the null hypothesis is true, right? And then we check with, just type that, we check with the significance level. So if it's less than the significance level, we reject the null hypothesis. And if it's above the significance level, what we say is we are unable to reject the null hypothesis due to lack of evidence. So we don't say that the alternate hypothesis is definitely true, uh, but we say that we don't have enough evidence, right? And so what this probability, right? What the probability of something happening by chance, the probability of something happening by chance is called a type 1 error, right? So for, let's say, for 20 heads, or like, or maybe like for three heads, right? Getting three heads in a row, the probability was 0.125 or 12.5%. So if in this scenario we accepted the alternate hypothesis, right? Uh, we can say that there's a 12.5% chance that we wrongly accepted the null hypothesis. That's why this is called the type 1 error. Similarly, type 1 2 error is the opposite of that. That is, you falsely accepting the null hypothesis or failing to reject the null hypothesis, but we will not get into too much of that for the time being. Right. So now let's look at another example, and I want to basically uh, relate this to everything else that we've covered. So let's say we have an example. Let me actually write that down for you real quick. All right, so here's the question, right? So Toyota cars have an average mileage of 20 miles per gallon and a standard deviation of zero point 0.5 miles a gallon. Toyota now claims that their new cars have upgraded technology due to which the mileage is greater than 20 miles per gallon. Uh, we get a sample of 20 Toyota cars with a mean mileage of 22 miles per gallon. So what we have to do is perform hypothesis testing using a significance level of 0.05, and we assume that the population is normally distributed. So we have to prove whether uh, their their claim has some substance or if it does not. So first things first, right? Um, we identified what the null hypothesis is, right? So our null hypothesis is that the mean is equal to 20 miles per gallon. And we also assume that this is true for the time being. Our alternate hypothesis is that the mean is greater than 20 miles per gallon. Sorry, miles per gallon. Uh, right. So now we have a sample with a mean of 22 miles per gallon, right? So how do we test this, right? So we have to find the probability, and this is very similar to how we've been doing sampling distribution problems previously. Uh, we have to check the probability of getting 22 miles per gallon, uh, and then compare it to the significance level. So uh, we have a sampling distribution of size 20, right? And the mean of the sampling distribution is going to be the population mean, which is 20 miles per gallon, because we are assuming that the null hypothesis is true. Uh, and we want to see that 22, what's the probability of getting 22 by chance, as opposed to there being some other reason. So mean is 22 miles per gallon of the sampling distribution, and the standard deviation of the sampling distribution, also known as standard error, uh, that is going to be our this of the population divided by under root n, which is 0 0.5. So we have the population standard deviation. If we didn't, we might have to use S to estimate, and for that maybe we needed a sample size greater than 30, right? Or if we didn't, we'd use the t distribution, all that stuff that we've already covered, right? So under root of 20, and let's just quickly see what that adds up to be. Sorry. That ends up being around 0.112 approximately. That is our standard error. So, what is the probability that we get 22 miles per gallon in the sampling distribution? So, how many standard deviations are we away from the mean here, right? So we can do that. 22 minus 20 divided by our standard deviation, standard error 112, which is equal to 2 divided by 0.112, which is 17.85 standard deviations away from the mean, right? So 17.85 standard deviations is a huge number of standard deviations for something that would be normally distributed, and the likelihood of us getting 22 miles per gallon, assuming that the null hypothesis was true, is close to zero. It's close to zero. So uh, the probability of happening is so extremely low uh, similar to getting 20 heads in a row, uh, that and it's well below the significance level we have of zero point 0.5. Therefore, we reject the null hypothesis. And that is just about how you would solve any kind of question like this. Is essentially you would get the probability of something of your sample having that result by chance, right? uh, and that is how you would solve any of these questions. The only difference could be you might have to deal with a t distribution scenario, or something else, right? Or maybe you're using s as an estimate and just knowing, like, similar to how you do confidence intervals basically. And that's about it.